Hello, welcome to another session of NICER 201, ICMR NIE's online course on causal inference from observational studies, or COSIT in short. Today's session is about confounding. I have divided this topic into 3 short sessions. In the first session, I'll be talking to you about what confounding is and how does it occur in any epidemiological study. The second session, we'll address how to take care of confounding in epidemiological studies. And in the third session, I'll walk you through certain examples of this process of identifying and addressing or eliminating confounding. So let's get started with the first session on what is confounding. If we look at the big picture, the overall goal or purpose in any epidemiological study is to find out if an exposure causes an outcome in a particular population. We are trying to understand whether a particular factor causes a particular outcome. What we want from these studies is the causal effect of this exposure on the outcome. However, when we design and the way we design epidemiological studies, what we get from the studies itself is what is called as association. And sometimes it's possible that the association that we see may not actually be the real causal effect that we want from our studies. This can happen because of random errors or errors that occur due to chance. And this can also happen due to what are called as systematic errors or various kinds of biases that can occur in any study. The best way to make sure that in an epidemiological study, we get as close to the causal effect, the intended causal effect as possible, is by doing the study through the process of what is called as the counterfactual. I have talked to you about the counterfactual in my earlier sessions. However, just to recap, if you're in an analytical epidemiological study, what we do is we have 2 groups. We have one group which we say as exposed and the other group which is not exposed. Or depending on the design, it could be one which is the disease and one which we don't have the disease. And then we try to compare the distribution of the exposure and the outcome in these 2 groups. So ideally, in terms of the principles of causality, what we would want is to know what would have happened to one fixed group during the same fixed time, with the only change that is happening is the exposure. So at the same time, in the same population, they may be exposed at one point of time, and at the same point of time, with nothing else changing, they may be unexposed. And then we would like to see what is the difference in the outcome that we achieve. Now, this is what is known as the counterfactual approach. The reason it is counterfactual is that because in reality, we will not be able to achieve. So we modulate this counterfactual approach by having 2 study groups during a fixed period of time, the same reference time, same study time for these 2 groups, and we compare the outcomes and exposures in these studies. At this point of time, in order to understand why confounding occurs, we also need to be aware of another principle, which is called the principle of exchangeability. What that means is that exchangeability is that the unexposed group exhibits the risk that the exposed group would have had if the exposed group had been unexposed. In simple terms, we know that there's an exposed group and an unexposed group, and we get an outcome from the exposed and the unexposed group. Now, if we exchanged the exposure status, so we make the exposed group as the unexposed group and the unexposed group as the exposed group, if everything else is fine, we should get the similar distribution of the outcome in the 2 groups. And this is the process this phenomenon is called exchangeability. So how does confounding happen? So basically, confounding is a bias, and it's a bias in the estimation of the effect of the exposure on the disease occurrence. And why does that happen? Because of a lack of exchangeability or comparability between the exposed and the unexposed population. what this would lead to is a confounded estimate of the causal effect, the true causal effect, which will of course not be equal to the actual causal parameter of interest in the source population. Let's look at this from numerical perspective. This is an example where we're trying to compare the actual observable populations with the counterfactual. This is from paper by Greenland and Morgenstern. So here, if we have population A, a study population A, which is in reality exposed. Now, in order to know the causal effect of that particular exposure on the outcome, ideally, we would want to have a counterfactual population from the same population A, which should not be exposed at the same time as the population is exposed. Of course, that's not possible in real terms. So what we do in epidemiological studies is we try to have another group of people who are unexposed to this particular exposure. Now, here what we have done is that we've taken this unexposed group, which is denoted by x equal to 0, from another population. If we consider the population B, where in reality the participants are unexposed, in order to know the true effect of the exposure, we would actually need a counterfactual from the same population B, where the same individuals in that population would be exposed. So if that was the case, so in population A, considering the counterfactual, the risk of outcome in the exposed in population A, in x equal to 1, would be 30%, which is 30 who are exposed and who have the outcome denoted by y, where y is equal to 1 is outcome present and y is equal to 0 is outcome absent. So risk of the outcome in the exposed is 30 by the total individuals exposed, which is 100. So that's 0.3. And in the same population, that is in population A, among those who were actually unexposed, in terms, which is again in a counterfactual manner, the risk of the outcome among the unexposed would have been 20 divided by 100, which is 0.2. So the true causal, in order to measure the true causal effect, we could either take the risk difference, the causal risk difference, or the causal risk ratio. So the causal risk difference, the true effect would have been 0.3 minus 0.2, which is 0.1. And the risk ratio, the true causal risk ratio, would have been 0.3 divided by 0.2, which is 1.5. Similarly, in population B, the true causal risk difference would have been 0.2, which is 0.3 minus 0.1. And the true causal risk ratio would have been 0.3 divided by 0.1. However, since when we have actually done the study, we have taken the exposed group from population A and we've taken the unexposed group from population B. And now when we calculate the risk difference or the risk ratio, which becomes a measure of association because that is the observable contrast between the two populations, we would find that the estimated risk difference would be risk of exposure in population A minus the risk of unexposed in population B. So that's 0.3 minus 0.1, which is equal to 0.2. And this, on similar lines, the risk ratio would have been 0.3 divided by 0.1, which is equal to 3. Now we know that in population A, actually the true causal effect in terms of the risk difference was 0.1, whereas it's 0.2 in the study that we have done. Similarly, the true causal risk ratio is 1.5 in population A, but the association, the estimated risk ratio that we get is 3, which is again different from the true causal association. So here what that would mean is our risk difference and our risk ratio measures are actually confounded. Now, why are they confounded or biased? Which means they are not the true estimate of the true causal effect. And that is because we have taken our unexposed group from population B, which is actually not the same as the counterfactual that we would have wanted from population A. So population B is actually not the correct population to have selected your unexposed people from. And that has led to this process of confounding. What we would also say that these two populations are not exchangeable, and hence that is leading to confound. We've talked about confounding. So the next point is, what are confounders? So confounders are essentially extraneous variables, which means the variable other than the exposure and the outcome, because what we are trying to know is what is the effect of the exposure on the outcome. Now, there may be other variables or other factors because of which the study exposure group may differ in terms of its probability distribution for the outcome. Not because of the difference in the exposure, but because of the difference in the distribution of these extraneous variables or third factors, as we may call them. And these extraneous variables or third factors which lead to this confounding would be known as confounders. So how do we go about identifying these confounders? In the sense that we've said that these confounders should have these three characteristics, right? The confounding factor should be an independent risk factor for the outcome. The confounding factor should be associated with the exposure, but it should not be in the causal pathway between the exposure and the outcome. All of this relationship between the exposure, the outcome, and the confounding factor, these are ascertained through what we would call as prior knowledge. And that information would come from basically the existing literature and other studies that have been done in relation to the particular exposure and outcome of interest that you may be doing your study on, the relationships between these particular confounding factors and the outcome and the confounding factors and the exposure. So it's essentially about what we already know from literature, from the context in which we are doing the study, from probably our experience of dealing or looking at these variables. And that is what would help us and guide us to ascertain these relationships and the direction of these relationships between the confounder and the outcome and the exposure. This is all for this session. In the next session, I'll talk to you about how to address confounding. Thank you.